Okay, so some people were asking, so before I get into the index, let me rewrite this estimate, and people were asking how you actually really see all the, when you use that solution, how do you see the inequality of scalar curvature, mean curvature, and the dihedral angles. So you have something like this. Scalar curvature. This is over n. And then you have the mean curvature. This is the pullback as well. And then you have the dihedral angles. Sorry, this should be the other way around. The boundary term goes away because of the boundary condition. So now, it is a concern. You say, well, if this is H1, how do you dominate this? You're restricting to a codimension 2 object. Well, the estimate goes like this. So this is going to be 0, and this lives in H1. With the boundary condition. And you know in H1, you can approximate by things that are smooth and vanish near codimension 2 things. Okay? So these guys vanish near the angles. By approximation, is this clear? H1 norm is less than 1 over m, let's say. And these guys vanish. Plug this in here.
So where did they come from?
This?
Yeah.
H1 space. Codimension 2 has capacity 0. So plug in m here. You see this term, this term, this term, all controlled by H1 norm. So okay, this term disappears. So then you just go to the limit. That's it, right? Is this clear? Just you have this. So now go to the limit. Goes to 0. You see this term. This implies this is 0. Okay. So you in this inequality, you see that you go to the limit. You see scalar curvature has to be the same. Mean curvature have to be the same. But how do you see the dihedral angles? But now it's smooth. So now plug this back into the original estimate again. Okay. So that's the proof. Is that clear? So I just want to emphasize, yeah, all these here is controlled by H1 norm, so it's okay.
Then
Are we good? Yeah, so now Here comes the real business. Okay, so we need to find that solution. So with these, let me just repeat again. The key important to compute the index is the dihedral angles. So if n is less than the corresponding dihedral angles of m, which is assumed to be less than or equal to pi. That's the assumption. Okay, the other conditions are, for this index calculation, actually, it turns out to be not so important. So let me just state the really key condition here. Then this Dirac on this twisted Dirac on this bundle with the boundary condition B is essentially self-adjoint, Fradon, with domain given by this and I'm kind of merging two sort of results into one. The point is, of course, what we really want to see is the index of the relevant operator is exactly this degree of f times this, and we know it's non-zero by assumption, our assumption. So this is what we want. Now, you can think of these as this is the sufficient condition to guarantee that we do know how to compute. Now, in theory, it's possible that even without these conditions, even with this, you have some Prandtl operator that computes the right index. You just have to pick the right one. It's possible. But then it gets very complicated because we really want to keep track of the sort of spectral property and things like that. And so in this generality, this is the sort of most reasonable geometric condition to keep track of and to make sense of this. And these conditions allows us, there's actual work to do, yes. Essentially, this allows us to compute the index. Okay? Is this statement clear? All right, so before I go into this is a part of the proof actually takes most of the bulk of the paper. So it takes, there's quite a bit of a computation, of course. So I will not go into all the details. But first, let me outline sort of the key idea, how you actually compute the index, provided we accept, these analytic properties. Let's look at the square. So intuitively, you have a theorem operator on this with the correct boundary condition. You say, well, it computes the Euler characteristic because the theorem operator is Gauss-Bonnet in two-dimensional case. So in this case, you really think about it. It's in some sense, well, of course, for this object, this guy right here, Gauss-Bonnet is known. There are elementary proofs. So for this object, it's kind of saying we go through all this, how many pages of work just to reprove the Gauss-Bonnet by using the theorem operator and the boundary condition. So, okay. But in some sense, actually, as I will try to convey, the most difficult technicalities actually lies in dimension 2. Okay, and that's where the most complicated things, the analysis we need to do. Well, we'll get to that. But so the rough idea is this. From an index theoretical point of view, you just look at this operator. In this case, let's just theorem on differential forms with the boundary condition, which is in this case absolute boundary condition. Let me remind you, in this case, it means if you have a differential form, you write it as the tangential part and then the vertical normal part. And this just means that when you restrict to the boundary, this is 0, the Dirichlet boundary condition for that component. Directly computing the index of this appears to be difficult, but if you have a smooth object, you have a ball, say, or think of this as, if you have the standard disk with the smooth boundary with this boundary condition, that's classic, okay? So that's done. So this, in this case, classical with this boundary condition. So in this case, is indeed, well, let me just forget about the map, let's just think about the theorem operator itself, okay? So in this case, two-dimensional disk, which is 1. So what we need to do intuitively is you're just gonna smooth out the corner. You just, or intuitively you think of, here's a corner, it's 90 degrees, just, push it open to 180 degrees. And then for each corner you do that, it makes it like an object like this, right? You guys kind of smooth it out, like something like this. But that's good enough, it's a smooth object now, so it's the same computation that gives you index 1. So the difficulty is, how do you make sense of going from here to here? Okay? And that's what we're going to do. So it involves the fact that we need to show, this is a typical thing you do in index theory. You want to compute something, maybe the original object, it's the metric or whatever, it's difficult to compute. You want to change it to something else that you know how to compute, and then there's a homotopy between, and you want to show the index remains invariant under the homotopy. Yes?
Is it straightforward to show that the index is invariant here because
that's the difficulty. Yeah, we need to. The homotopy is one of the key steps, and to show why you can do the homotopy to make sense of this. Yeah, so 2 steps. Yes, exactly. Yes. So, yeah. So because when I say push it open, then you are changing the boundary condition too, because of the you can imagine this. The angles are different now, right? So that's part of the difficulty. Yeah. On a closed manifold, it's essentially trivial to see that if you change the metric, of course the index remains invariant, right? Well, because there you don't need to deal with boundaries. Now, smooth boundaries, even if you change the metric and the boundary condition will change accordingly, in that case it's not so difficult either, because the changing is in a smooth way. And here, that's exactly what happened. The change is not smooth at that corner. Yeah.
General Dirac operator, the boundary, where's first time the index was calculated?
For the Dirac operator, I mean, I would say, Gauss-Bonnet is the first index theorem, but of course it was stated not using theorem operator.
Right, post Matthias Singer,
You mean if the first
have a manifold, it's a compact manifold, a smooth boundary, smooth metric, whatever you want. I want to know the index of that thing.
With the boundary though? Yes.
Yeah.
Yeah, I mean, I would say still Gauss-Bonnet probably is the first example. This,
right, but like,
who computed the first one?
Is there a paper that like does a kind of Matthias Singer with a smooth boundary in the 70s or 80s or something?
Well, first of course the classical series paper Attia Patoli Singer, that's the APS boundary condition. But if you are thinking of this, of course this work is done in some sense, this Chen, this is called Chen-Gauss-Bonnet theorem. So Chen, but of course he doesn't use the operator, he does it in an intrinsic way. But anyway, the theorem, if you want to really think about the operator like this with the boundary condition like this, I don't know, I cannot pinpoint which is the first paper, but it's definitely, there are plenty of textbooks that everything is written down, for example. Just one example, Gilkey, has a textbook on, I think it's just called Attia Singer index theorem, something like that. And he has a chapter on the theorem operator and the boundary condition like this, and then do the computation and actually gives you, computes the, So that kind of.
Like Locke's recent paper.
For him, I mean, he just needed to, for the smooth case, he just, to actually, the index is that, say the Euler characteristic, that's how I think he just quoted, I mean, that's done. So the point for these results is, if you have a smooth boundary, you already know what the index is. It's just, now you just need to get the estimates. That's, Does that make sense? Okay, so that's the strategy. So we just need to, in this calculation, we need to take care of the corners. Okay. Say it again?
There was a type, like an angle in the first version of the paper.
In the first paper, we do have this assumption, but somehow we omitted this assumption.
Do you know if that breaks the index thing, or is it just a...
Without this condition, the index, if you choose, without this condition, this, we essentially show that this is if and only if. With this condition is the if and only if. Essential self-adjoint is corresponding to this condition. Okay, I'll write down explicit. Now, without this condition, it's not going to be self-adjoint, but turns out this analysis is based on conic singularities, conic metrics. So it's going to be fratom, although in general, without this condition, it's not going to be essentially self-adjoint. So you have a lot of self-adjoint extensions to pick, and it will give you different indices. So if you pick the wrong one, then you're not going to get the right index. But also because, then it gets delicate. Since it's not essentially self-adjoint, you can pick a fratom extension, but then the domain is also not this anymore. So you have to be very careful. So now we want to show something is self-adjoint, or essentially self-adjoint. As you know, you have an object, you want to show some operator is self-adjoint. But this can be done in a local way by partition unity. For example, you have the square here. I can try to analyze if it's self-adjoint here, if it's self-adjoint here, if it's essentially self-adjoint here. I hope that this picture makes sense. And now for codimension 1, if near smooth face, essentially self-adjoint, that's classical. So we know. So for example, in this picture would be, well, when is it essentially self-adjoint in this corner here? So look at the theorem operator, which is this. And basically we say, suppose you have an angle like this. It doesn't have to be 90 degrees, of course, just some angle. What the geometric situation, what we have here is actually, you have two angles. You have the target, the domain to compare, and this angle is alpha, this angle is beta. And the setup is, we have this assumption. But now let's forget about this for a second. Let's just say we have some angles, right? Alpha and beta, whatever, right? And then we say, when we just ask ourselves a question, when is this operator in this corner here? When is it essentially self-adjoint? So let's actually decompose this calculation in several steps. But now here is sort of the key abstract sort of criteria for us to tell whether some operator in this, I should mention that the typical metric we deal with is conic. Now you say, well, what if it's in dimension 3? Well, then it will be a fiber-wise version. So even you say, in dimension 3, along this edge, of course, it's going to be an edge cross bunchal angle. So it's a fiber-wise version. So it really, near the dihedral angles, is still a fiber-wise picture like this. And the analysis, you can just do it fiber-wise. Okay? So in the conic metric case, here's, so let me write in, let's still focus on this case. This is the operator, and then yeah, so before that, when we do calculus, sometimes it's easier to, if we write, this is a conic metric, and I would prefer to write it in terms of cylindrical coordinates, just change by some coordinate change, essentially by opening this up by some bundle unitary. Okay, so once you write into the cylindrical coordinates, looks like this. Let's say this is the dr direction, and then this is the theta direction. Okay, so. And cylindrical coordinates, you will see the dr term, and then there's 1 over r term that corresponds, because the original guy is the conic metric. So you have p and p. Now p is the operator, that's just our notation, it's the operator on the link along this guy. Roughly speaking, it's the theorem, but it's a theorem plus a little bit something. So according to its own, it looks like this, okay? D theta, D theta. There must be some sign over here. Where's the negative sign? Yeah, okay? It's just change your coordinates. You write down the operators. It looks like this, okay? So now here's a little lemma, which says the following. In this setup, this is essentially this result goes back to Shiger, Bruning, Seeley. Quite, a lot of people have worked on conic metrics, of course. This is one of the first lemma, that you sort of encounter when you decide whether something in a conic metric, that operator is essentially self-adjoint or not. It goes like this. This is essentially self-adjoint if and only if the operator on the link. Of course, to be precise, if you have a boundary condition here, so of course this guy would have a boundary condition. So, but roughly speaking, it says this is essential if and only if this operator, the spectrum is at least 1/2, sorry. So the spectral gap has to be at least 1/2, and then this is the if and only if. It's done by a very explicit, in all dimension. In all dimension. So, well,
Is there also an angle condition?
no, if this is very abstract, I don't even have to state, it doesn't have to be this operator. It's just, some geometric differential operator is essentially self-adjoint if and only if in a coordinate metric that operator on the link, the corresponding operator on the link that I written down like this in the cylindrical coordinates, if and only if that operator has spectral gap at least 1/2.
That's achieved by the hemisphere somehow?
By the yes, we'll see. The pi is going to be, that's exactly this condition is going to achieve this in the two-dimensional case for this operator.
So what does essentially mean?
Oh, essentially self-adjoint. So okay, in a self-adjoint extension, and people yes, you have a formal self-adjoint operator, and you say it has some self-adjoint extensions. Essentially self-adjoint means there's only one extension, which means the minimal extension is the same as the maximal extension. There's only one. That means it's essentially self-adjoint. So yeah, in this case, you see, there's only one choice, and that's it's good that when you don't have to make a choice, then okay, things are okay. In this case. Yeah.
I've studied the stuff for drag operators for like the hydrogen problem. So Lyman has sort of theorems like this. Do you know if there's anything similar that you're doing, but what Lyman has done in that context?
Yeah, I mean this lemma, for example, can be done. That's actually that's already done by quite some time ago. A student of Chiga Chao, for the Dirac operator. So then in that case, it's related to. So for the Dirac operator, you want to have the Dirac operator on the link has spectral gap 1/2, and the natural condition would be you have enough positive scalar curvature. So, yeah, okay. But yes, this can be definitely, this has been done in a Dirac context. This has to be done for the signature operator and so on. And what Chiga, I think, where kind of all this started with him was he was concerned about the signature operator. Okay, so let me write down the lemma. So, and then you will see why these conditions. So in our case, and maybe just say in our case, in this setup, you have an angle alpha. So let's pick the simplest case, same angle. And let's see why the condition less than equal to pi appears. So in this case, you're really looking at just one arc, right, of angle alpha, and then it's this operator here. In this case, if that's the same angle, then the boundary conditions, if you translate these boundary conditions, if you pull back the boundary conditions of these guys here, they would match up, right, if they have exactly the same angle. And we know that's just the absolute boundary condition. This is the standard one, So in this case, look at the spec. This is really an explicit computation in this case. If alpha is equal to beta in this case, okay? Suppose. You want to compute the spectrum of this guy. It's shifted by 1/2, so let's So of course you'll be shifted by 1/2, some here. So this is just what we've learned in calculus. You have on the line, you have Fourier sine, cosine function, you solve an ODE. So it's just compute. It gives you exactly this, where K goes from. That's the spectrum of that guy. In particular, this spectrum, or just look at this. Right? Because at 0, when K is 0, you already had negative 1/2. So you just look at when K is 1, you want to be to the right of positive 1/2, and then this guy should be less than that to achieve 1/2. And that's okay. That's in dimension 2. Okay, that's the. Okay, let me maybe keep this operator here. So maybe this is the first case, second case. Now let's look at the journal. Oh, just look at the journal case now. Alpha, not equal to beta. So now, a typical situation we are concerned with will be something like this. This is beta. So now, of course, you can line up the bottom edge. So pull back the boundary condition. They still match up. But now, over here, if you translate back, it looks like this. So now the boundary condition is, on this edge, is still the usual absolute boundary condition. On this edge, it's a sort of a mixed boundary condition. But we know what it is. You just need to write it down and do the same calculation. It turns in the journal case, is I've already simplified this 1/2 into the expression, so it's just that. Okay, now it's again just simple arithmetics that you want to make sure that the spectrum of this has gap 1/2. So you look at when K is 0 and when K is 1, and you want to make sure 1 is to the left of 1, negative 1/2, and the other one is to the right of 1/2, and then you do the computation. So, oh shoot, let me erase this. It's essentially, this is if and only if. You just do the arithmetic. This is where these boundary conditions, these angle conditions come in. So now in this case, you have essential self-adjointness. This is a case in 2-dimensional, yeah. Now here comes the higher dimensional case. So, and as I pointed, as I mentioned, in fact, and of course, it's going to be, as you can imagine, it's going to be an induction process. So it turns out most of the calculation, what we need to do is actually really compute the spectrum, is in this case. In a higher dimensional case, before I write it down, let me just say, in a higher dimensional case, if you look at a link, in this link, it's essential that because this link is a circle, it's just an arc, it's flat itself, so it doesn't carry any curvature. But in higher dimension, if you look at the link, it's a 2-dimensional sphere. It's a three-dimensional sphere. The link itself, it's positively curved. You are positively curved, so to get spectrum gap, it's much easier. So there actually you don't. So once you have this, in higher dimension case, in that, so from that geometric sort of point of view, it's actually easier. But of course, you have to do some computation. Yeah. Does that make sense? So what I'm trying to say is
The only like issue with the angles of the dihedral type meeting, you know, but in higher dimension, those don't matter
because
can you just re-explain why they don't matter?
in the three-dimensional case, the link is a two-spherical. Link is a two-dimensional spherical sector, right? No, we've already taken care. We've already taken care of the. You probably are worried about this part. Is that what you're worried about?
Yes.
We've already taken care of this, right?
We took care of the 2D case, right?
But it's a fiber-wise case. This is.
But like, so this is up until the angle goes to. So this is another question, but we know like fiber-wise it's self-adjoint when each angle equal to blow up. Like each angle is at those pi. But like your angle is probably not constant, right?
Yeah.
And then your estimate there is very like borderline. So the error terms not matter. Like if you're approaching pi and then lifting up pi and going back pi.
Yeah, it's okay. So this, to be precise, this lemma is it's a fiber-wise type argument. So fiber-wise is okay, everything's okay. So now you're saying if it's, just to be sure, you mean along this edge when you go down, it's not constant. Is that what you mean? Along this edge, yeah. Along this edge is okay. It's a really, it's as I said, it's a fiber-wise argument.
Sure, but it's a non-constant angle, right? So like you do have error terms as the angle varies.
No. So for the essential self-adjointness, this theorem says if in the fiber-wise case it's like this. If this is essentially self-adjoint, if only fiber-wise, it's 1/2.
The big one is self-adjoint if and only. Oh, that one is
Fiber-wise.
the left. The one on the left is that all. That operator is defined
On the whole thing.
Dimensional space or the two-dimensional?
Yeah, on this thing. Yeah, it's three-dimensional. Yeah. Okay. So this part is taken care of. I hope now it's clear. So now we need to go down, or codimension go up one by one. So now you are looking at a vertex in three-dimensional case. Now it's a link. It looks like this, the picture I drew over here. So the link now itself is positively curved. Now, at least intuitively, you would believe me that you want to make something has spectral gap. It's, in some sense, it would be easier. Okay, now here's one technical thing that where the induction is used. When you look at this operator P, now on the link, two-dimensional link, P operator itself has corners, has dihedral angles, right? But these dihedral angles, because this sphere, so the boundary conditions, so these angles are exactly the original. So for example, in this picture, if I draw a sphere, you can draw the sphere vertical to these, perpendicular to these edges. So these will be just the original dihedral angles. But by the previous step, the angle condition already tells me that this operator P on this spherical triangle, it's already essentially self-adjoint. Yes, I can talk about its essential self-adjoint extension. I can talk about its spectrum. So you want to calculate the spectrum of this along this face, and you want to make sure it's also has a spectral gap at least 1/2, and then you'll be done. Okay.
But why is the triangle the only thing you care about?
Why is the triangle the only thing?
Like, why is it sufficient to know that the P defined on the triangle satisfies the spectral gap? What about the operator on the rest of the corner?
This one?
No, the vertex. Like
Here?
the bottom left.
Here?
Yeah.
No, that's exactly what we are trying to use this to get, because now the new D in three-dimensional case, let me call this fiber F, and the link is L. We've written again. You just do the same thing again. And this is the new operator on the link. So you just run the conic analysis one more time.
Oh, right.
So, because now this is the link, that's the vertex. It goes in like that.
So, that's true for any conic metric, which could be any dimension, right?
Yeah.
Completely general.
Yeah. It's the proof is spectral, so it's not really, you would say, okay, this is not really a manifold, closed manifold. It has its own corners, and the link itself doesn't have a smooth boundary, but that's okay. By induction, it goes like this. It's almost like you first prove the two-dimensional case is essentially self-adjoint by this analysis, and now use the fact you've already proved the two-dimensional case is self-adjoint, and calculate its spectrum, which is at least 1/2. And then you use it to show that three-dimensional thing is essentially self-adjoint, and use a three-dimensional thing to calculate the spectrum, it's at least 1/2, and keep going like this. Well, if it's already at 1/2, then you have to be careful. That's exactly why you have sort of the extreme case, and you cannot go beyond. Go beyond pi, not a self-adjoint, not essentially self-adjoint. Yeah. You're saying, yeah, that's so the paper we do this. This is also standard. You don't have all the analysis will work. You don't have to be exactly in the strictly conic case. Asymptotically conic is okay. So I was going to not mention this, but yeah, so. But this can be done, okay? Asymptotically. So in other words, you probably some saying, when this angle goes in, maybe not exactly, it can have a little bit, but it converges to the conic, but itself maybe, there's some wiggle. That's okay.
Is that also singular, or is that different?
It's really essentially the same proof, but maybe the details you can find it in Guoliang and Xie. Yeah. Yeah. I mean, we repeat, for what we needed, it's also repeated in the paper anyway. Yeah. Does that answer? Yeah. Yeah. If you prepare, so the point is, it's. I would say it's closed, but it's open to one side is open. You perturb it inside towards. If you squeeze down, angle becomes smaller than pi. That's okay. So inside, away from pi, it's an open condition. It's only pi is the extreme point, and then you just don't go beyond pi. That's all we need to be worried about. So, and then in the process, you just don't go beyond pi. For the essential self-adjoiners, these error terms don't matter. It's a lower order term, essentially.
Sure, that's it.
Yeah, that's the yeah. So no, but it is one has to be. But this is a standard thing, as if you work with conic metrics. Okay. But of course, I would say if you write down all the details, yeah, one needs to write down all the details, sure. Okay. All right. So let me just say.
This is very non-technical, but like,
Yeah.
there's nothing particularly interesting about being able to do less than or equal to pi versus strictly less than pi, is there?
I mean,
In terms of the angle, dihedral angle condition, right? Like the theorem is stated for angle less than or equal to pi,
yeah.
and I'm saying that, but strictly
Yeah.
less than pi is almost a very similar theorem, is it not?
Well, if you believe, if you're really talking, so it's just whether you allow degenerate dihedral angle. So whether you consider smooth is also, it's just a minor thing, sure. I mean, if you do assume when you say dihedral angle, it really has to have an angle, then yeah, you just say less than pi. Yeah. So let me just say, yeah, so the third step is in higher codimension. It's by this geometric observation. Maybe, what time? How much time do I have?
You started a bit later, so I think you've got
Okay.
10 minutes.
Yeah, we need to start.
Okay, that's okay. Okay.
Aim for 10 minutes. If it's 15, it's fine.
Okay. No, I think I'll be okay. So let me make a sort of so the geometric intuition here is exactly what I said. In higher codimensions, it's more positive curve, so it's actually easier to achieve this condition. So it's an explicit computation. And if you've seen, for these sort of Bachner, Weizenberg estimates, and this is, you have some, standard estimates you can write down. But I do want to point out on the link here, this operator P is not the theorem operator itself. It's the theorem operator plus a potential. So P is the theorem operator on the link plus an extra term. As you already have seen, in the two-dimensional case, there's a potential. By that I mean there's an extra diagonal term like this, d theta. So here is also some diagonal term, C0, C1. These numbers L, something. Depends on the degree, of course. These are just some numbers, depends on the degree of the form, and I can write them down, where Cj is 1 minus j, depends on the degree of the form, j minus L minus 1 over 2, where L is the dimension of this, in this case, L is 3, and so on. So there's some extra term, and this extra term actually is important in the X curvature estimates, or the spectral estimates for this. But once you take this into account and do the computation, you do show, in this case, you always have this. So the dihedral angle condition is only used in dimension 2, and to get essential self-adjoiners for these things on the link, and then you just run the induction. This step, actually, you don't really, at least on the surface, it doesn't really use the dihedral angle condition. But of course, it's hidden in the induction process. Okay. Where does say it again?
How come these show up in higher order?
This the sort of down to earth sort of thing is you just when you write down in terms of cylindrical coordinates, you just see them. Okay.
1/2 analogs?
Yeah.
Okay.
Yeah. And a conceptual explanation is these coming from. You can think of this as a twisted Dirac operator, and this is some extra curve. It's a different connection. This is responsible. Actually, you are working with a slightly different connection. So this, if after these 3 steps, and then that's essentially it. This proves, now you just run, and then this proves the essential self-adjointness altogether. This altogether implies DB, the original guy, is essentially self-adjoint. This is essentially self-adjoint, and the fraterness is the standard thing that you just, with this kind of conic analysis, you get fraterness on the nose. Okay, so this is you just have it. Okay, so in fact, it turns out even if it's not essential self-adjoint, every extension that you have in this for the conic, this sort of thing, you always have fraternal operators. But we do need essentially self-adjoint, and it will be fraton. Now, for us to get the domain is because it's essentially self-adjoint, so it's equal you just take the minimal extension. Then the minimal extension, the domain is exactly this smooth functions satisfy the boundary condition, and just complete. You get H1. So this will give you also. This implies domain is H1. So now, once you are in this case, and then we go back to what I mentioned earlier. So there is definitely there's another key step to show is once you are in this setup, how do you show the operator when you change the boundary condition, when you change the angles and so on and so forth? Why does the index remains unchanged? So let me give you instead of going through all that details, again, let me give a sort of conceptual explanation. So now, I want to compute the index on this, which has corners. So I have 4 corners. Let's cut it out. Cut out these 4 corners. So you literally pick out, for example, a picture like this. So now, this is local enough. You would put some matching boundary conditions over here. This is local enough, you can show that on this piece, put the right boundary condition on this end, you can show the index on this piece is 0. Well, if it's 0, if it's 0, and then this analysis tells you it doesn't matter which angle you put there. If it's 0, whether it's pi over 2, whether it's pi, well, why don't we just replace it by pi then? So now you are in this case. Well, this, of course, in this I used it's something we proved that we need to prove that this process cut and glue. It does this gluing formula makes sense. It does make sense. Of course, it needs a proof, but it can be done. So now replace this corner, smooth it out. This is just a smoothing process, and just do it for each corner. Now you're back in a smooth case. You didn't change the index, and you're done. And that's the argument. Okay.
Questions? This last step no longer needed. Assuming a sine yourself as doing this for whatever reason, this last step doesn't itself need the angles anymore, right? To be less than or equal to pi. Assuming itself is doing this. If you go for whatever reason.
Yeah, the way we do it, we do use the geometric condition, but yeah, I mean, abstractly, as long as you can guarantee that the two pieces that the index of this and then index of this is the same. And so basically, this is, let me make it sound fancier. It's like a surgery for conic metric. So you can cut it out and put something back, right? As long as you keep the index. So it's like a surgery for, conic type metrics.
But you somehow use the angle in your actual surgery.
Yeah, so because the way we do it is we show that this thing has index 0. So this is using the angle condition. So we show actually it's 0, and this thing also has 0 index. So when you replace it, because this is actually, maybe it's related to what you're saying. What if you have a fiber version? So on just this one guy, it's very explicit. I just compute it. But if you have a fiber version, and now I want to say it's, if the metric is kind of weird, and then I don't know how to, because that's the one I want to compute. But if it's weird, then I don't know how to compute it directly. So I need to somehow say, well, what if it's 0 then? If I can just show it's 0, then I'll be okay. So that's what we did. Yeah.
For the domain person showing that you're just before the corner when you do this part directly, then you don't have to consider.
You mean you just cut it out?
Yeah, cut it out and then you're saying that those two pieces are actually have the same index. That would mean.
But you created some new angles. Is that what? You cut out, you have new angles. You do want to glue back. You really want to get rid of all the angles in the index computation. So just glue something back, which is nicer.
So I guess one basic question: how do you actually compute the index of this particular guy?
It's an explicit estimate. You show it's invertible, so it's 0.
But how do you do that?
We have in this, for example, in the 2-dimensional case, you see you really write down something very explicit, and it's just you compute it. So this can be done. It's a very explicit thing. Yeah, you just compute. So
people have done this, I guess, a lot, right?
I don't know. I don't know if this is in the literature, but I mean, it's something. It's like calculus. It's not that technical to compute this part. Just to show that this is invertible. It's not technical. Yeah, higher dimension. Yeah, there's a little. One has to be slightly careful with how you do induction, but yeah, exactly. So you just, in the 3-dimensional case, you would like to cut out this corner first. Okay, you have to do it in the right order, because if you cut out this piece first, you will be in trouble, because you create something that's the dihedral angle is greater than pi, and that's bad news. So just do it in the right order. Cut out this corner first, and then so on and so forth. And then so that's, remain in the world of dihedral angle less than or equal to pi. Then that'll be okay. And that can be done in the right order.